Hey, this is Brock Lemire's Embedded Systems Design. We are looking at the SPI interface on the MSP430. And in this video, we're going to look at an example where we transmit a packet over the SPI as a master, and a packet means just multiple bytes. And we're going to use a interrupt to track when one packet has been sent and the next one can be put into the transmit buffer. So this avoids a situation where you have to actually put manual delay loops in your program. Okay, so let's take a look at the assignment in front of us. Here's the packet we want to send. So I want to send F0, 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 and then 40. Okay, and I just made those numbers up. You know, you can put in whatever you want, but that's how we're going to do it. And remember that to set up the SPI, what we have to do first is we put the thing in software reset, and then we configure everything. So we're going to try to get a 100 kilohertz S clock. So to do that, we're going to choose SM clock as our source, 1 megahertz. That's our bit rate clock. Then we'll pre-scale it down by dividing by 10, by putting 10 in the bit rate control register. And then we'll accept the default values for the framing options and the clock polarity. So that means it's just going to look like a standard SPI where it's rising edge, or the clock is low when it's not sending, starts with a rising edge and pumps the data out on that rising edge, and the receiver receives it on the falling edge. And we'll use 8-bit LSB first as our framing options. And what we're going to do is drop information into the transmit buffer, and it will automatically shift out. But we need a way to know when we can put the next one in. So we're going to use the transmit complete flag, which is UCTXIFG. Okay, so what this flag does is it watches the transmit buffer, and when it's finished sending the last byte out, so it's shifted everything out and is ready for more data, TX will assert. What's cool about this is that to clear the TX flag, you actually write to the transmit buffer. So this is how the UART transmit flag worked too. So when we drop a byte into this register or to this buffer, the flag will clear, and then it will assert when the data is shifted out. So we don't have to we don't have to manually clear this flag. Okay. All right. Of course, the transmit flag, if you can raise a flag, it can generate an interrupt. So you have an interrupt, which of course is this is a peripheral, so it's maskable. The register is the UCTXIFG, so that's the flag register. Keep in mind, this is the exact same spelling of the flag registers for the UART, except that when you are in SPI mode for a peripheral, they take on different values. And so the SPI system actually only has 2 interrupts. It has a transmit and a receive, so it's a lot simpler than the UART. Then, of course, those 2 interrupts have local enables. And then, of course, with all of these peripherals, they have this interrupt vector, which is just a prioritization code. If you happen to have multiple interrupts that fire at once, you can look at this and service the highest priority. We're not going to use that because we're just implementing 1 interrupt. Okay, if it's got an interrupt, it needs a vector. So the vectors, remember, all 4 of the serial communication peripherals on the MSP430, FR2355 have their own vector. We are going to use A0 because that pumps it out to pins on the launchpad board that are really easy to probe. And here it is. So it's called EUSCI_A0 vector. And you can see in here, here's where the UART flag is, RX flag and TX flag. And notice that these are SPI mode. And notice they share with the UART. That's because the peripheral can either be UART or SPI. And then in the case of the B0, B1, which are on a different page, they can either be SPI or I2C. So each peripheral, each serial peripheral only gets 1 vector. Okay, so we just got to know. But for this example, it's no big deal. We're only going to use 1. Okay, now let's choose A0, which brings out its its SPI signals to port 1, bits 4, 5, 6, and 7. And we won't use the serial or the slave transmit enable, and we'll set up the slave out master in pin just because usually you don't have a one directional bus. You usually have a link, a full duplex. So we set it up, even though we're not using it in this example. And the 2 signals we'll observe are we'll look at P17 and P15, and that'll be the clock and the data out, and then we can watch this packet come out. Okay, so that's what we're going to do there. All right, and now remember, we're kind of using, we started packet transmission, And so we need a way to start it. We don't want to use a timer to start this. Well, I mean, you could, but we'll use a button press on switch 1. And when we do that, it will drop the first byte into the buffer, and then we'll use the transmit flag to notify another interrupt service routine when it's ready for the second byte, then when it's ready for the third, and when it's ready for the fourth. Okay, so we have to have 2 interrupt service routines in order to make this work. Okay, so let's do it. Let's fire this up, and here we are. Okay, so I'm going to create a new CCS project, and we'll call this C_SPI_TX. This is our second example of transmitting. And we'll do a packet on A0 with TXIFG. Okay, and so then here's our code. Okay, there we go. There's our skeleton. So the first thing we want to do is clear out that header. And then let's do this. So let's set up A0 for SPI. And first thing we do is put it into software reset. So we put A0 into software reset. And so we come down here. And that is done by setting a bit in the UCA0, CTLW0, the A0 control word register 0. And I'm going to bitwise OR with a mask UC software reset. And that puts it into software reset. Okay. Now let's configure the clock. So we'll choose SM clock, and then we will set prescaler to 10 to get S clock equals 100 kilohertz. So the prescaler will be 10. All right, that we select the clock in the UCA0 control word 0 register. And we go ahead and bitwise OR it with a mask called UCSSEL. And then __ SM clock. So that chooses the 100 megahertz S clock, or the 1 megahertz S clock as our original clock. And then we go into the bit rate word register, which is UCA0 BRW, and we just drop 10 in there. And that 10 will divide the 1 megahertz clock by 10, and it will give us a bit rate of 100 kilohertz. Okay, now let's do some setup for the SPI mode. So I want to do put A0 into SPI mode, and first we do that by going into the UCA0 CTLW0 register. I'm going to set a bit that's called UC sync. That puts us into synchronous versus asynchronous. So that flips us from UART into SPI. And then the next thing we're going to do is we are going to put SPI into SPI master mode. Okay, we do that using this bit in the UCA0 CTLW0 register. So we set the UCMST bit, and now we're in master mode. At this point, we'll accept the default values for the clock polarity and in behavior, and also the framing options. So we don't need anything more with the SPI. So it's actually ready to go. Okay, so now let's do the configure the ports. So I'm going to configure the ports. And so in this situation, what I'm going to do is I need to tell the port function select registers that I'm using the SPI bits instead of the port bits. And so I'm going to do it like this. Let's go ahead. Actually, you know what? Let's do that in a second. Let's set up the push button switch. So that's on make port 4-bit 1 an input, and that's SW1. So we're going to set up that interrupt, because that interrupt is how we're going to start the packet transmission. So let's go to port 4 direction register, and we'll make it, actually we want a 0 there. I'm going to go boom, bit 1. Okay, so that's what makes it a input. And then we'll do port 4 resistor enable. So let's go ahead and enable the pull up, or the pull. We don't know what it is. So this will be enable resistor. And then we'll go to port 4, and we'll use the secondary function for port 4 out. And we will set bit 1, and that makes the resistor a pull up. So make resistor a pull up. All right, and then since we're going to use an interrupt, we got to go port 4 interrupt edge sensitivity, and we'll go ahead and set bit 1 of that one. And what that does is it makes the interrupt sensitive to high to low transitions. And that's how the behavior of the switch works. When it's not pressed, it's pulled up by the internal pull-up resistor. When I press it, the single pole signal switch shorts it to ground and gives me a 0. And that edge is where we want to trigger. All right, so now we're back to the port function select. I'm going to type this out a little different. I'm going to go port 1, SEL1, and I'm going to clear the first bit, okay? And I'll go bit, and then I'll fill in the number in a second, okay? So what I want to do is I'll label these like this. I'm going to do port 1 bit 5 equals S clock, okay? And we need to use the 2 port 1 select registers simultaneous in order to get the setting. And so what the value that I need to write in here is 0, 1. So I'm going to do that by saying port 1, I need to clear bit 5, and then I need to set bit 5. So I clear bit 5 in this register to 1, and I clear it, or I clear it in select register 1, and I set it in select register 0. And that sets a value to 0, 1, and it chooses the function S clock for port 1. Okay. Now I'm going to copy and paste that. What I'll do is I happen to know that on bit 7, that is going to be slave in master out. And so then all I have to do is change that to a 7, and I got it. And then I'll come down here, and then I know that bit 6 is slave out master in, and then all I have to do is do this and this. Okay. All right. So that's how I kind of copy and paste those and maybe save time. Okay. So that's the ports or the IO, but I got to turn on the IO. So I got to go to power module 5, CTL 0, and I got to clear the lock low power mode 5 bit. So I got to turn on IO, and then I'm ready. Okay, so now what I got to do is take out of software reset, and I'm ready to roll. Okay, so I'm going to come up here, copy this little buddy. Boom. Boom. Okay, so there's the software. There it is. Okay. All right, there we go. Nice. All right, so now what we're going to do is we're going to enable IRQs. Okay, so we got 2 of them we got to enable. So the first one is going to be, let's do the switch. So let's do enable port 4-bit 1 IRQ local. And so that one will be port 4 IE, and I'm going to set the bit 1. So that enables that guy. And then what I'm going to do is I'm going to clear the flag. So I'm going to go to port 4 flag. I'm going to clear bit 1. And there we go. So I clear the flag. And so those are almost ready to go. I have to do the globals, but I'm also going to enable the UCA0 interrupt enable. I'm going to enable the UCTXIE. Okay. All right, so that will enable the A0TX IRQ, and then let's clear its flag. Even though I know I don't need to, I have to. UCA0 IFG, and I'm going to clear it. So I go ampersand tilde UC IFG, UCTX IFG. Okay, let's look at these flags here. So UXTX IE, UXTX IFG. Okay, that's good. So clear flag. All right, so those are all ready, and I just need to do enable interrupt, and that does the globals. So then enable global, and it didn't turn purple. Oh, there it did. It did turn purple. Okay, so now I'm sitting there, and I'm ready to do while nothing. Okay, so there's my main loop. And now all the functionality is going to be handled in service routines. So the first thing, now we're ready to actually, all we've done is set everything up. So let's go ahead and add the functionality. I'm going to create a global variable. I'm going to create 2 global variables. First one's going to be the packet. And I'm going to do the packet using, I'm going to call it packet. And what I'll do is I'm going to initialize it with F0 hex, and then I'll do F0 hex, and then I'll do F0 hex, and I'll do 040. And you can do whatever you want here. I need to have these in as a global variables because two interrupt service routines are going to edit them or alter them, use them. And then I need to have a position variable, which is going to track the index of this array right here. So I'll use this global variable called position to be like, oh, I'm in position 0, send it. Position 1, send it. Position 2, send it. Position 3, send it. So that's how we're going to do that. Okay, here we are. So now we're ready to do our interrupt service routines. So go ahead and do this. So these are my ISRs. And the first one we're going to do is let's do the switch. Okay, so let's go ahead and do the switch. So what happens when I want to set up the switch first? So I'm going to say pragma. Okay, this tells the compiler, excuse me, compiler, I'm setting up the interrupt vector. Please go to port 4 vector and put the starting address of the routine that comes next. The routine also, by the way, is an interrupt, so please return from it using a RETI instead of a RET. So I'm going to call this ISR port 4 underscore S1, and then I'm not passing anything in, and then we'll go ahead and do this. So what do I want to do in here? What I want to do is this. I want to initialize position. So I'm just going to put 0 in there, and then I'm going to put the first byte of my packet into the transmit buffer, and this will send it out. So I'm going to write to UCA0TX and I'm going to drop in there. I'm going to go to my array called packet, and I will give it the index position, which is 0, and this is going to send first byte. And then that is it. So we have to clear a flag, which we do by doing this, and there's the interrupt service routine for the button press. So if I press that button, it's going to go ahead and drop the byte into the transmit buffer. It will shift it out automatically. And when it's done, the transmit flag is going to set, and we will then trigger an interrupt that I'm going to write the service routine for right now. So let's go to pragma, tell the compiler, excuse me, I would like to also now set up the EUSCI underscore A0 vector with the starting address of the following routine. By the way, the following routine is an interrupt that you need to return from using an RETI. Okay, so A0, okay, and nothing in, nothing out. Okay, so now we're sitting here, and now we got to think about what we're doing here. So the first thing I'm going to do is I'm going to increment position. Okay, so this gets me to the next byte in the array, and now I need to, essentially the logic is going to be this. I'm going to go UCA0 TX buff is going to get packet at position, so that index, and that will get the next word. So I increment it, and then what I'm going to do is just drop the next byte into the transmit buffer. The problem is we need to also track when we're done with the packet, so I have to put some logic in here. So I'm going to give you a little logic that's different from what we've done before, but here's what I got to do. I'm going to increment position, and then I'm going to check position. And I'm going to say, you know what, if you're less than the size of the packet, then you can go ahead and drop something into the transmit buffer. Okay, that'd be nice. And then if you're not, go ahead and disable this thing. Okay, so now I'm going to sit here and I'm going to say A0IFG, and I am going to clear it. Okay, so I'm going to do this by clearing the TXIFG flag. And let's think about why I'm going to do that. I could disable that, but if I clear this flag, no more information. So basically what happens is I won't put anything into the transmit buffer. Okay, and then I can clear the flag, and that will leave me in a state where I'm ready to go to the next time the button's pressed. And that's different from what we did before with the UART. In the UART, we actually disabled the interrupt, but in this case, this will work also. It's just a different way to do it. So when I'm still working through the packet, I just drop the next packet in and I'm done. And then otherwise, I don't put anything in there, which basically ends the packet. And then I go ahead and clear the flag to get back into the state that I want. Okay, that is it. So let's go ahead and do this, and let's save this up and clear some typos. Okay, so we go ahead and fire up my board. And let's see what kind of errors we got here. A lot of errors. Okay, so unrecognized pre-processing on 62. 62, pragma, should be pragma. And then TXIFG is not, yeah, of course that's not, it's UC. Anybody else? All right, so there we go, save those buddies. We'll go ahead and fire this up. Errors exist, let's see what's going on now. Recognize preprocessor 62, did I not save? Pragma. I do pragma. Okay, here we go. All right, life is good. Life is not good, actually. I forgot, I messed one thing up. So the reset, I had a bitwise and. I need a bitwise and. We got to clear this bit to get it out. So I just realized that when I tried to run that, it didn't work. So go back and change this to a clear, but using a bitwise and with a tilde on the mask to invert it. Okay, so that'll make things work a little bit better. Okay, so let's take a look at the board. So here's the board. We're gonna look at the clock and data on port 1 bit 5 is the clock, port 1 bit 7 is the data. And so I went ahead, I'm using the analog discovery oscilloscope, and I put channel 1 on clock, channel 2 on data, and then I put both of the negatives on ground over here, and then I grounded the analog discovery to a ground pin there. And so now we're ready to roll here. So let me stop, let me recompile this and download it again, and then we'll take a look at the measurement. Okay, so now it's there. So now let's do this. Let's move this down here, and I got waveforms, which is my software to run the oscilloscope. So I'm going to have this on here and I'm going to move the trigger around here, and then I'll go ahead and hit run, and now it's sitting there waiting. And I go ahead and hit go, and nothing's happening, which is what we expect. We have to push the button. So now I'm going to come back to the board and push the button and see what happens. So I'm going to go ahead and press it. Oh, there it is. Okay, so now notice that it's kind of coming and going. That's because we're running in continuous mode. So we actually just want to run in single mode, so that the scope arms, and then when it sees the trigger, it will then trigger and run one time. So I'm going to hit single, and then I'm going to press, wait for it to arm. I'm going to hit single, and then I'm going to hit the button. Okay, and you might have to do it a few times, because what will happen is that when you hit single, any trigger condition on the scope will cause it to trigger. And sometimes if you slide your board around, you'll actually get a little ESD buildup that'll cause it to do it. But I got a packet right here. I got something on here. So let's stretch this over here. Now let me do it again to try to get more on the screen. So single, press the button. Okay, so I got more data on there, and that looks like about it, right? So let's make this so that it's I can see both of them at the same time. So let's go ahead and come over to channel 1, and we'll make this 1 volt per division, and we'll make this 1 volt per division. And then I'll go ahead and I'll put the data up here, and I'll put the clock down here. Okay, so this is cool. So look at this. I got, how many clocks should I have? I should have 32, right? So 1, 2, 3, 4, 5, 6, 7, 8, 32. So that's 32. And then I get a bunch of data in here, which kind of looks like what I should see, I guess. At least it's doing what it's supposed to be doing. So let's see, I can zoom in, zoom out a little bit, and this is pretty cool. So let me do it on this zoom level. So single, boom, single, boom. Okay, this is awesome. All right, so now yeah, that's awesome. Okay, so now let's see what that data is. So let me go to the screenshot that I took and I annotated. So this is the same data, right? So here it is. I have the clock on top, but this is 32 clocks. And so if I put the little zeros and ones on there, that's what I get. But remember that they're LSB first. And so you can see that this is like 1, 2, 3, 4, 1, 2, 3, 4. So 0, 0, 0, 0, 1, 1, 1, 1. Well, that's, if you flip those bits around, that comes out to be 1, 1, 1, 1, 0, 0, 0, 0, which is this, and that is F0. And so it's kind of a distinguishable pattern. So it's like F0, 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 and then what's this one? 4 zeros. Well, that 4 0 hex, that happens to be all zeros and then followed by a 1 if you go LSB first. Okay, so it's working. So that's pretty cool. So now let's do the logic analyzer. So I'm going to go back to my board. I'm going to pull off the scope, and then let's take our logic analyzer and put that on port 1 bit 5, and then that on port 1 bit 7. Okay, so I got that. And now let's do go back to welcome screen, go to logic, and we'll go right away. We'll go ahead and say enter a SPI bus, and we want select is none, and we want the clock is on 0, data's on 1, it's LSB first, rising edge, that's fine, 8 bits, show it in hex, okay. Remember, for a trigger on this one at 100K, let's go ahead and make this like less than 6 microseconds. Okay, so now let's go ahead and I'll do a single and then hit the button. Okay, so look at that. I got some data right there. So let me zoom in on it and see what I got. Holy moly, look at that. Look at this. Let me run it one more time. So I'm gonna go single run, and that cleans it up because the little sloping rise times were just due to the zoomed out too far, and it was connecting the dots. It only gets so many dots across stream. But look at this. So now I have F0, 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 40. So I get to see the actual data. Then I get to see it decoded, which in this just simply means flip the LSB to the LSB position. Okay, that's it. This is awesome. So we did it. You know, it's kind of interesting. It's like you can't even to try to get 2 of these on the screen would be almost impossible because you'd have to press the button twice. You'd have to do like single and then press. So awesome. You did it. All right, so that's it. So you just set up a SPI master transmit of a packet this time, not just a byte, and you allowed the transmit complete flag to tell the program when it was ready for the next packet, and you did all the transmission using interrupt service routines. All right, nice work. As always, remember to support my channel by subscribing and